Right, good morning everyone. What I want to do today is I want to go back and have a look back at vibrational spectroscopy, and I'd like to look at an example from vibrational spectroscopy, and then that is the case where we can find a force constant, and then I want to go to rotational spectroscopy and see if we can't find a bond length. So I'll just remind you that solving the one-dimensional Schrodinger wave equation for a particle for pair of particles connected by a spring in a harmonic potential gives equi-spaced energy levels. So the energy levels are spaced, but of course, in reality, we have molecules being represented, diatomic molecules being represented more by a Morse potential. However, the bottom does approximate, so the fundamental vibration in the Morse potential approximates what we have in the harmonic case, so we can use that result, that the difference in energy is h bar omega, but of course omega is k over root mu, and we can express it as a wave number for spectroscopists who are going to work in 1 over lambda. So if we have the vibration from experiment, everything is constant, the reduced mass we can figure out from that, and we can calculate the force constant for a molecule. So here's an example that I would like to have a look at, is that I did some digging on the web, and I found in some databases, I found that the strongest fundamental vibration transition for 35Cl2 is 554 centimeters to the minus 1. So calculate the force constant of the bond. So just think what we've got. We've got to have the reduced mass to be able to sort this out. So if we've got the reduced mass, we can go in here. And we need the wave number. Yes, we've got the wave number, but the problem is that it's not in SI units. So we in centimeters to the minus 1. So we maybe need to fix this number, the fundamental vibration, to convert to meters to the minus 1. Pi, speed of light, is fine. Mu, we've got to calculate from the chlorine atom. Okay, so I think with these we can maybe try and proceed and see if we can calculate the force constant for a 35Cl2 bond. Okay, so firstly of all, I've had a look for isotopes of chlorine on the web, and I was able to get an exact value, which I'm only representing here to 2 decimal places for the mass of a chlorine atom. So the reduced mass for Cl2 is going to be 1 over the mass of one chlorine atom plus 1 over the mass of the other chlorine atom, which is just 1 over 34.97 plus 1 over 34.97. But of course our answer is in grams per mole. Of course, what we could do is we could change it to kilograms and divide by Avogadro's constant. But on the sheet I've given you, I've got a conversion factor. So look at the table of constants, and you can just use that conversion factor if you like. The next example, I will calculate it the other way. It's fine. And I get the reduced mass of a system to be 2.903 times 10 to the minus 26 kilograms. So if I go back, so we have managed, in this case, to calculate the reduced mass of chlorine. So we've got mu is there. We now need to just make sure that our fundamental vibration is sorted out, and we can rearrange into the algebra to find K. Okay, so we have the reduced mass for the Cl2 system. Now let's see what we can do. Now, of course, remember, if you're going to convert from centimeters to meters, you're going to divide by 100. But of course, if you want to convert from centimeters to the minus 1 to meters to the minus 1, you have to multiply. Remember, this is a wave number. So the way I'd like to think of it, just imagine you've got 1 centimeter. In that 1 centimeter, you've got 554 wavelengths in that centimeter. So the question is, how many wavelengths would you have in a meter? And well, there are many more wavelengths in a meter than there are in a centimeter. You're going to have to multiply. And so if you multiply it by 100, you'll get 55400 per meter is what you have for the strongest fundamental vibration. Okay, so now we have everything we need to do this calculation. We have the reduced mass, we have the wave number, and don't lose sight of what we're trying to find. We're trying to find K, the force constant for the bond. Okay, so um, now it's just a matter of rearranging. So of course, I've taken 2 pi c, that's on the bottom, taken to the other side. So here's the 2 pi c, and then times by the fundamental vibration is root k of mu. And of course, I've simplified that down to 1.044 times 10 to the 14 is root k over mu. Now, the easiest way is to square both sides, and of course, this horrendous 10 to the 14 becomes a 10 to the 18 per second squared is k over mu. And of course, I'm trying to keep all units apparent. So when I put the reduced mass, I'm going to put its mass in kgs, and so I'm going to bring, so k is simply going to be this number times the reduced mass, and when you multiply that out, you get, from these horrendous numbers, you get something quite reasonable as 316.2 kilograms per second squared. So this is fantastic. We know now the force constant for a 35Cl2 bond. Okay. Now, it'd be interesting that if we were to explore other isotopes of chlorine, we could have a look at 37Cl2, look up those exact masses. But the interesting thing is that 35Cl2 and 37Cl2 are identical chemically in terms of the electrons. So the answer you're going to get is going to be you would start off with a different fundamental transition because they're heavier atoms, but the result would be the force constant for 37Cl2 would be the same. So just bear that in mind, that you can change the masses. If you change the masses of the atoms at the end of a spring, but you don't change the spring, the force constant is going to remain the same. Your fundamental vibration may change, but the properties of a molecule are going to remain the same. Okay, so that there is calculating K from spectroscopy. Okay, so that's the first problem I wanted to do today. Second problem I wanted today is have a look at a rotational spectra and see if we can calculate a bond length from rotational spectroscopy. Okay, any questions so far? Okay, just interrupt me if you have a question, or just type it in on the group chat. I've got half an eye on that at the moment. Right, so I just want to remind you in terms of rotational spectra is that rotational energy levels are quantized. You can't just have any rotation in a molecule. Those levels are quantized, and we see that in experiment. We see bands of absorption in experiment. It's not absorption at any energy level, at any wavelength. There are specific wavelengths that are absorbed rotation by molecules. And these energy levels are given by Hc times the product of rotational quantum number or rotational quantum number plus 1 times this constant b. And of course, if we put naught into here, the j into j plus 1 is naught. If we put 1 into here, this becomes 2. If you put 2 into here, it becomes 6. If you put 3 in here, it becomes 12. And so we see that the energy levels are spaced 0 to 6, 12, and 20. I've put it on a backdrop of graph paper. But of course, B is this rotational constant, which is dependent on the moment of inertia of the molecule. So B is h over 4 pi ci. So this is useful to us because it relates, we know that the difference in absorptions we see here, the difference between this absorption 0 to 1 and this absorption 1 to 2 is 2 hCb. the difference between this absorption and this absorption is 2hCV. The difference between this absorption and this absorption is also 2hCV. So in the spectra, the wave number, if we convert that to wave number, the difference in energy is 2hCV, but the difference in wave number is simply 2b. So from the spectra, we can calculate B, and from B, we can calculate the moment of inertia. From the moment and from that, we can calculate the bond distance. So this is our procedure. As we start from spectroscopy, we look at the spectra, and we know that the energy difference between these is 2hCV, but the actual difference in wave number is 2b for each of those. And so from the 2b, we can calculate B. From B, we can calculate I, which is the moment of inertia. If you know the mu, the reduced mass from atomic masses, then you can calculate the bond length of a system. Okay, so there was a problem on the previous slide. You didn't hear clearly. So what I'm trying to summarize on this slide, I'm going back. So just to summarize on this slide is that these are the energies, these dark lines are the energy levels for rotation. Okay.
Sorry to disturb you, Prof. It's
Yes?
slide 23.
Slide 23, this one. Sorry, was this the slide that's problematic?
Yes, Prof. Can you please explain the conversion part?
The conversion. Going, oh yes, it's a tough. So if I told you to convert, say, 5 centimeters to meters, you divide by 100, and you go 0.005 per meter, you would divide. But I just want to highlight, this is not centimeters you're trying to convert to meters. You're trying to convert centimeters to -1 to meters to the -1. Okay, so what does it mean, centimeters to -1? It's centimeters to -1, you can view it as being per centimeter. How many things there are fitting in a centimeter, and these are wavelengths. These are the number of wavelengths that fit in a centimeter. So if you can imagine, a centimeter is a really small unit of length, and we can fit exactly 554 wavelengths of that light, or that vibration, into a centimeter. So the question is, how many would we be able to fit into a meter? Well, there are 100 centimeters, so we would be able to fit 100 of these into a meter. So to convert per centimeter to meter, you simply times by 100. Does that clarify?
Yes, Prof.
Okay,
Thank you.
so just be careful. Be very careful in converting from centimeters to the -1 to meters to the -1. It's a multiply by 100, not a divide by 100. Okay, and then work through the calculation. If you get something that's order of a couple of hundred of kilograms per second squared, then you know you're in the right ballpark for force constants. Okay, now we're looking at rotational spectra, and for rotational spectra, we have this rotational constant that we can get from the spectra. We can calculate the moment of inertia, and of course, if we have the mu from atomic masses, we can easily get the bond length. So here's an example. So for HCl, this is gaseous HCl, the rotational bands are separated by 21.12 centimeters -1. So calculate the bond length. And again, we have this problem, is that we have a non-standard unit. We're going to have to convert it to meters to -1. So you can imagine that we can fit in a centimeter 21.12 wavelengths in a centimeter. So in a meter, we can fit 100 times that amount into a meter. So to convert from centimeters to -1 to meters to -1, we're going to have to multiply by 100. Okay. So just don't look at the whole slide. We're going to look at this in parts. Okay, so what we've got over here is our spectra over here. So just have a look at the spectra. And on the right-hand side over here are everything we need in terms of the relationships between everything else. We've got our reduced mass equation. We've got our rotational constant, which we can get from the spectra and hence calculate I. And then, of course, we're going to, once we've got mu on this side and I on that side, we're going to use have a look at the moment of inertia that we've got over here. So I'm going to deal with B first. So let's deal with B first. So B is 21. 2B, we've got this distance between the bands as being 21.12 centimeters minus 1, which is the same as 2112 meters minus 1. So we know that the distance between these is 2B, and so I just divide to get B. So all this is converting to meters minus 1 and dividing the 2B that we get from here by 2, so that we've got the rotational constant for the system. There's a question, will you be given these formula on a formula sheet in a test or exam? And the answer is yes. But can I just qualify it? There's one formula that I want you to be able to derive. So there's one that I may or may not give you, and that is for particle in a box. Okay, so all the others will be provided to you because we haven't been able to derive them, but particle in a box is one that I do want you to derive. Okay, so you will have these available to you. And so the question is, can we use what we have available to calculate the bond length? So you're happy that from the spectra, we recall that the bands are 2B apart. And so we've got the rotational constant is 1056 per meter. Okay, now we know what B is. We've got to rearrange with all these constants to find what I is. And so if you take B as being that and you rearrange it, you can put an H bar, looked up H bar from the table of constants, 4 pi, speed of light from the table of constants, and I'll be in here. I calculate I, the moment of inertia, to be 2.65 times 10 to the minus 47 joule second squared. Okay, and that is so that is the moment of inertia. Okay. We can convert, and that is the same. I've just really got over here. This is the same number here. I'm just trying to show in this line that it is the same. The joule second squared is the same as kilograms meter squared. Is the units we really want to be placing in I is equal to mu r squared. So it's nice to know that we don't have to change anything in terms of a number, that the units do work out totally correctly for us to take this further. Okay, so we have on the one side, we have got the I that we need. What we need now is a reduced mass. And so I've looked on tables, and I've looked on tables to just check what the exact atomic masses are for chlorine 35 and for 1H. And so the reduced mass, I found the reduced mass in grams per mole. I've then divided by 1,000 to get in kilograms per mole. And I've divided by Avogadro's to get it in kilograms per particle, per molecule. So the reduced mass I get there is 1.63 times 10 to the minus 27. Just note that because you've got such a light atom, which has mass 1 gram per mole, notice that the reduced mass is dominated by that light thing. You can imagine that chlorine is like a bit of a wall, and the vibration is really being handled by that poor little hydrogen atom that has been thrown back and forth. This is a case where you've got a really heavy atom, very light atom, and so your reduced mass is dominated by the light atom. Okay. So it's ever so light, slightly less than the light atom, but it is the light atom is dominating that term. So what we've got over here is we've got I. We've calculated I, we've calculated mu. And so if we know I and mu, then of course we can try and just rearrange, and I've taken mu, I've rearranged to get what R is. R is square root of I over that, and I get, put that 2.65 in, put that 1.63 in, and I get a R is 1.28 times 10 to the minus 10 of a meter. That's 1.28 angstroms, which is exactly in the ballpark for bond lengths. Okay, so these are two problems. The results from quantum mechanics for vibrations and the results from quantum mechanics for rotation are incredibly useful to us because both of those results, the energy results, have resulted in us being able to calculate force constants for bonds and bond distances as well. Are there any questions? Okay. I want to have a look at the hydrogen atom tomorrow. Well, I'm going to look at something slightly before the hydrogen atom. So it's a big section. I don't want to split it up. So I don't want to start on that today. So I'll give you an opportunity for a couple of questions. Okay, if there are no questions, then we'll meet again tomorrow at 11 o'clock. Okay, right, thank you.